Hi, good morning, and welcome to the ZP Developer Zone. So we like to do this Developer Zone once a week, and it's really just answering technical questions that have come in during the week. So let me jump straight into it because we've got lots of questions to get through. So today's the 27th of October. This is a live streaming webinar, though it's always recorded. So if you're interested in what we do here, just come along to the recordings later on. Question number one, the detection of lead. So this won't all be about just slides today. I do have some hardware in front of me. I'll try and do some demonstrations, though I'm running a little bit short on sensors at the moment as well. I do have some more coming, but that said, I have some, let's say, older sensors that I can possibly do at least some sort of demonstration of the workflows, but my pristine sensors, I'm a little bit short on them. But that said, I do have hardware in front of me. Now, the reason that hardware in front of me is relevant to this conversation this morning is because if you're familiar with the Sensor platform, it's a very different kind of potentiostat, if I can say. And one of its features is this ability to use QR codes to either do, I want to say normal analytes, so normal analysis. When I say normal analysis, things like amperometry, open circuit potentiometry, linear sweep voltammetry, impedance spectroscopy, cycle voltammetry, differential pulse voltammetry. And then it also has the capability of being analyte specific in terms of, let's make a biosensor for lead, let's make a biosensor for nitrate, let's make a biosensor for potassium, let's make a biosensor for testosterone. But that will all become a little bit more clear as we go through the webinar this morning. I'm also conscious that time is quite short, so I want to go a little bit quicker. So let me just do that now as well. So we've talking about the detection of lead in water. Also, somebody was very interested in a Streptavidin modified screen printed electrodes. So I will talk about that this morning as well. I'm just grabbing something to my side here that I'll need. So that will be discussed very shortly. We'll also discuss about molecular imprinted polymers, MIPS. MIPS are they're quite popular. We have done quite a lot of MIPS work ourselves at ZP. It's an interesting technique. I mean, it holds great promise, but I must admit it's hard to get right, if I can put it that way. But anyway, I'll discuss a MIPS paper this morning, and that MIPS paper will be for detection of this Cyromazine, which I think, if I remember rightly, is a pesticide. I will also, let's see what else we've got on the list this morning, talk about creatinine detection on gold screen printed electrodes. One of the things at ZP, I talk about it a lot in our webinars. I think that's something that's holding back a lot of academic research, or just research in general, but is the irreproducibility of screen printed electrodes. There's lots of vendors out there on the market that will sell screen printed electrodes. I think actually people are using these screen printed electrodes, or maybe producing some in-house. And the biggest issue is from electrode to electrode, they're not reproducible. This means it holds back the research. It means people start having to come up with things like calibration in situ, which is an absolute nightmare because it makes for a complex assay. So I will talk about the reproducibility of our gold screen printed electrodes. You'll see some data today that says that the RSD, the relative standard deviation of our screen printed electrodes, is like 3%. Somebody else was just interested in how does a creatinine sensor work? How does a vanadium redox flow battery work? A VRFB. I will discuss it. I can't discuss how to make them. Making them is an electrochemical engineering problem. At ZP, we do a lot of programs where continuous pumping is in operation. And these are large programs where we've got mechanical engineers, electronic engineers, electrical engineers, electrochemical engineers involved. So I cannot describe the making. I can describe the science of how they work. I'll talk about electrochemical aptamers for YADA. YADA, I think, is a sort of biomarker for a particular bacteria. So I'll talk about aptamer sensors this morning as well. Also some questions about potassium sensors. Somebody's interested in measuring potassium in blood. So you can theoretically, and I have had clients use our potassium sensors in blood, and our potassium sensors are also for continuous usage. But putting a biosensor into a final application is not just buy a biosensor, click it in. At ZP, we're ISO 13485, so if we're going to be involved in the placement of our biosensors into clinical analyzers or things like, it could be the application for dialysis or something like that, then ZP needs to be heavily involved and large budgets need to be available. But I will discuss our potassium sensors today. Troponin I'll describe our Troponin I sensor for some university students, and I'll also talk about translation of an ink-jetted nitrate sensor into a final product. So I'll go through that in a minute. With the final product, it really does come back to, or rather with that nitrate sensor, at ZP we do have experience of turning open circuit potentiometric sensors into things like nitrate sensors. I'm going to follow a particular paper this morning because the Sensi-All potentiostat allows people to modify screen-printed electrodes to make them compatible, for example, with nitrate, which they can then analyze using OCP. So we've got an OCP, open circuit potentiometric methodology. That's amperometry. Let me just go across one more. That's the EIS, and you just need to get in on that. There we are, open circuit potentiometry. So I'm in Bluetooth connection with that. I can now run OCP on that. But what we have in our systems is actually, when I say our systems, there's a cloud system called Julie, where we have a data pipe which can actually process things like OCP into things like potassium or nitrate. So we do have, for example, or testosterone, etc. So we do have quite a technology stack at Zimmer and Peacock. Some people want to engage us just on a sensor. And some people want to engage us more deeply on our entire technology stack. I would answer the question that, or I would make the statement that ZP is probably one of the most matured technology stacks, from taking something like a biosensor and actually giving a meaningful number actually on a smart device. And we do all that via sending the data to the cloud, processing the cloud, and sending the data back as well. Anyway, that said, let me go forward. These are the 9 questions I'll be covering this morning, and I have to respect people's time, so let's go forward a little bit faster. Just to say, if you're interested in doing point of care diagnostics, and I think the Sensi-All potentiostat and Sensi-All platform for translation, for doing sort of potentiostat type experiments and turning potentiostat type experiments into final products, if you're interested in that kind of technology, then the Sensi-All webinar on the 25th of November will be suitable for you. We tend to do 2 webinars, one in the morning, one in the afternoon. We want to be inclusive, make sure that nobody around the world is left out from at least having a live experience. If you can't make it live, just register, and the webinar's recorded anyway, but the live experience is probably, essentially you can ask questions in real time, which we do answer. So people get in the chat and start asking questions, and I'm generally, well, not generally, I can definitely answer all questions around electrochemistry and biosensing in real time. Wearables is not something actually I'm going to touch on today, but at ZP we do have technology just over there, in fact, a large wearables technology that we are also able to leverage. Now, if you're interested in wearables, 5th of November, 1 in the morning, 1 in the afternoon, webinars. Any links you see I'll put underneath this video afterwards. I'll go forward a little bit faster now. Academic research. So I'm going to talk about 3 papers this morning. One on a pesticide, one on a nitrate sensor, and one on a bacterial related sensor. And this is really all about the translation of academic research into more impactful form factors. So my argument is most scientific papers finish at TRL 3, but actually if they were using this as a potentiostat and using the fact that this runs only off an app, and we've got the capability of turning raw signal into concentrations, actually they wouldn't finish at TRL 3. They could actually come up to a higher technology readiness level. And for me, that's really important, because 25,000 papers in the sphere of electrochemical sensing and biosensing are produced per annum. We can translate more of these actually into products. I'd really like us to have a kind of product output that was more like the apps on the App Store, where people are able to make products much quicker and get them onto the market. And that's effectively what we've developed at ZP. If you are interested in making the research more impactful, please come to the webinars on the 10th of December. Again, any links underneath, I'll put underneath the video. This is something as well, we haven't done this in over a year, but this is something that I'm, in fact, now we're about exactly 3 weeks away from actually. We're doing a live workshop in Norway on wearable biosensors, point of need testing. This won't be a workshop where it's talk, it'll be like 45 minutes of talk, and then 45 minutes in the lab, 45 minutes of talk, 45 minutes in the lab. So it's very hands-on. It's over the course of 2 days. I'll be giving it, and I'll put a link also underneath the video as well. Right, so question number 1, detection of lead in water and soil. Right, so I've, I'll just put a, I think I put the little comment here. So what we have here is, at Zimmer & Peacock, we're really good at electrochemistry in general, but then specifically actually electroanalytical sciences. So we've developed a system for measuring the lead concentration in water. Now, the way our system works is we can take the sample, run the sample, we grab the raw signal, we process the raw signal in the cloud, and we actually send a concentration back to the smartphone. That's really important. So what I like about the system is it actually allows us to get a kind of, we've got the signal, we've got when the signal was gathered. When I say signal, it's an experiment. Who gathered it, what time, what date they gathered it, geoposition on that signal as well. And we process the signal into an actual concentration as well. So that is a really, I think this is very powerful for traceability, let's say, in lead detection. I think this is also quite powerful for citizen science as well, because it's a very sort of, there's two levels to interaction with this system. You can have a very kind of, oh, well, there's a result, done, let's say, but you can also have a result where you can actually really dive into where that result came from, which is really good for sort of validation of, that signal's for real. So when I say a short demo here, let me just go to, the reason it's slightly short is because I'm short on sensors, and I'm also, I'm short on sensors, basically what it comes down to. But this will give you an introduction. So this is the Sense-It-All platform. Now the Sense-It-All platform was originally developed to be a way of releasing electrochemical assays onto the market. So the classic one that we have, I'll take my QR code, I'll scan this. At this point now, this device is in Bluetooth connection with, effectively it's a potentiostat, but it's also a type of product that you could genuinely give to non-electrochemists. And they can put their sample on there, get results, and they'll get a result back on their phone. Now I'm going to focus specifically on lead at this point. So let me just come into lead. So now we've got a lead sensor application running here. So what this means now is that somebody can, now this is not going to be a nice demo because these sensors are all, I want to say pretty old. I've got some fresh ones here, but I'm actually saving them for some, I want to say more analytical work rather than describing the workflow itself. But let me just grab a sample. Right, so let me put the sensor on. Let me put the drop on there. Now, because I don't have a lead sensor on me, in fact, I'm going to have to change target analyte here. So I've just changed target analyte, but it will allow me to actually do a demonstration for you. So I'm just going to call this, this will give me horrible data because the sensor's so old. All right, yeah, that'll do. Right, but it really does demonstrate. I can see I'm going to get horrible data because I can see these flat lines, which tells me that the signal is really massive and over the limitation of the machine. But I know all of that, so I can sort of talk you through it. But what just happened there was, rather than just running cyclic voltammogram and being left with cyclic voltammetry, I actually did run, in that case, a cyclic voltammogram. But what it's given me a message as, and I knew I was going to run into this, is it's upload complete. It says too high, dilute more. It's just guiding me that actually I got so much, the sensor's old, it's already got this analyte on the surface, so it's basically gone over the top, let's say. But what I want to do is I just want to go to show you actually what's happened here. So let me just change to here. what it's done in real time, it's actually sent my data up to the cloud. So I'm just going to go demo. I can have a quick sip of coffee as well. And then I can see my instrument, which is this particular instrument here. And then I can see all the experiments that have run on that particular instrument as well. So I have it there. I can see my data there. So as I say, I was expecting this to be, I don't want to say horrible. This sounds a bit strong. But it was going to be horrible because, and I can see the data here. Now what this system is doing is, it's gathering cyclic voltammogram, but I had so much analyte in the concentration it went a bit flat. But it's done an electrochemical experiment. I could have guided it to do an amperometric experiment, an open circuit potentiometric experiment, an electrochemical impedance spectroscopy experiment, linear sweep, cyclic voltammetry, square wave voltammetry. It could have done any of those. But what makes this really different is it's got a data pipe built into it. So what I mean by a data pipe is this, that we've analyzed the second voltammogram, and we've actually told it, let me just say, we've told it to do a filtration on the data, a filter on the data, though the data was so clean, I didn't really need to filter it, to be honest with you. And we've told it to analyze the data, and we've told it to fit it to a calibration curve, and then we've told it to show extracted values. And it's the extracted value, one of the extracted values actually got sent back, would get sent back to the phone. So in fact what it's done is, it's gone and found the peak height here, which is very flat because there was just too much signal. But it found the peak height, it's put it through the calibration curve and turned it into concentration. So in most scientific papers, they will do a calibration, they will absolutely will, and they will even have an equation. But the tools that they're using, or the instruments they're using, don't have this data feature built in, where actually the data's sent to the cloud, we process it in real time, and actually we get a result, and we can send that result back to the phone. So you imagine that if you're working on like a citizen science program, you can't expect these citizen scientists to interpret your differential pulse voltammetry, your square wave voltammetry, your open circuit potentiometric data. You can't expect them to interpret it. But if you come up with a calibration routine, you can program it into this data pipe, and it will actually give back the citizen scientist or the nurse or the doctor, depending on who your kind of first end user is, a, let's say, real result. So I described that as a kind of short demonstration of what we're up to. Question number 2, Streptavidin is a really, extremely well known in the world of biology. It's a good way of sort of coupling antibodies to surfaces, because Streptavidin is really good at coupling with biotin. Somebody was asking whether we had any screen printed electrodes that were modified with Streptavidin, and the quick answer is we do. And as I say, let me just try this for a second. The biotin then means that people can conjugate antibodies or whatever else. No, I say whatever else. They can conjugate materials to the surface. So the quick answer is we do have a carbon sensor, screen printed carbon electrode modified with Streptavidin. This is a personal comment for me. I think sometimes that actually I would suggest that people didn't necessarily, this is amazing coming from me, that if you want to buy a screen printed carbon electrode that's modified with Streptavidin, you're very welcome to do it. I think when you're building biosensor assays, I think you're actually better off buying, in the particular case of making antibodies or making Aptasensor modified electrodes, I think you actually have to build them up yourself. So I would actually say use the Zimmer Peacock carbon 501 electrode and build that Streptavidin layer yourself, or buy the carbon hyper value electrode from ZP and build up that Streptavidin layer yourselves. But if people are so interested, they can actually buy them already modified as well. This is the detection of Cyromazine. Cyromazine, this is a classical kind of paper that comes out in my particular world. And, when I look at this paper, it has a laptop involved. It has a large potentiostat. In fact, I've got the potentiostat up there. It's quite a bulky guy. It's not one from Zimmer and Peacock. And it's using screen printed electrodes. And when we sort of analyze papers like this, they're actually using MIPS. I mean, what I like about the electrochemical literature, electrochemical biosensor literature or electrochemical sensor literature, it is very practical. You know, that here they're generally trying to detect a molecule called Cyromazine, which apparently is a residue in fruits and vegetables, and they're trying to detect it through actually MIPS, molecular imprinted polymers. So I'd imagine that they're sort of electropolymerizing these MIPS in the presence of a templating molecule. It leaves this kind of hole or pore, and later on then when the Cyromazine binds, then they use that to let's say deconvolute the signal. So I do find these papers kind of useful. I mean, these papers, you know, follow the kind of same structure. You know, you've got your materials and your methods, and then you've also got your results as well. So at ZP, I mean, I put the word demo here, but it really comes back to the same thing. Well, not the same thing. So first of all, you know, in a paper like that, you know, they'll start off with a carbon electrode. So we've got two well-selling carbon electrodes. We've got hypervalued carbon electrodes, and we've also got the carbon 501, which has a more circular electrode on it. So the first thing that these people will do is they'll do cyclovoltammetry. Well, if I want to do cyclovoltammetry, I can scan the QR code and I'm into cyclovoltammetry mode. And that will allow them then to functionalize the electrode. Now later on, they actually want to analyze it by square wave voltammetry. So square wave voltammetry is a good technique for being, let's say, slightly more sensitive. Now I'm not going to do it again, but if you rewind this video about 3 minutes, you'll see that I did a quick demonstration there. And there I demonstrated that in fact what we have in this system is the ability to do a square wave voltammogram, send the square wave voltammogram to the cloud, put it through the data pipe, and turn it into a final concentration. So what I'm keen to do, you know, when I find that papers are interesting or the target that they're trying to target is interesting, is say we can take a paper like this, or a paper like this could be done in a slightly different way, where in fact the same procedures were performed, but they were performed on one of our electrodes. I would suggest the 501 in this particular case. The drop goes on there. They use the QR codes to, you know, essentially drive the potentiostat. But then the potentiostat actually gives the data back, in their particular case, square wave voltammetry data back to the app. And the app sends it to a system called Julie. So Julie, I think, is really the only commercial data management system specifically tuned for electrochemical data. So that data comes back to Julie, and then we actually put the data through a cloud system through a data pipe system where we process the data, we put it through a calibration factor, and then we actually send a result back to the cloud as well. So we have all these procedures that can take place, and then actually what it means is we end up sending a result to the phone. So in fact, rather than finishing as papers do with, oh, here's my calibration curve, here's my raw signal. No, actually you can give it, in this particular point, the paper originally comes from Turkey, so you can actually start giving it to, like, you know, the environmental agency and actually having them, you know, try it out in real time. So, I mean, the current situation is that, you know, this paper is reflected by, this is a case study that I use where actually, you know, if you read these kind of papers, you know, they've all got a heading, a introduction, materials and methods, maybe mechanisms. And, you know, this is a kind of essentially a kind of template for papers that would appear in the electrochemical sensing, electrochemical biosensor space. But they all finish at technology readiness level number 3, which means, you know, we did a proof of principle in our lab, and that's the kind of end of our work. And, you know, my argument, you know, and I'll make, you know, argument, but the philosophy actually at Zimmer Peacock 10 years ago was to say there's a large body of actual academic research. It's not getting onto the market. There's 25,000 papers and more produced of the type that kind of I read per annum. And in fact, we can get more of these papers actually onto the market if people will start adopting things like the Sensi or potentiostat. Of course, you know, that's a biased opinion from me, but this potentiostat and the way it operates and the way it's actually got the mindset built into it that actually we want to get people to market is actually built into it. It hasn't come out by accident. This has been a sort of 10-year journey for us at Zimmer and Peacock. Right, so if you're interested in what I just mentioned there, it's probably worth knowing that we do an academic webinar. The next one will be on the 10th of December. Any links that pop up now, I'll also put them underneath the video. Question number 4, somebody wants to make a creatinine sensor. They want to do it on a gold electrode. They're very interested. Hopefully they've been watching some of our webinars because they're very interested in the comment about reproducibility. At ZP, this is actually some recent data. I just mentioned the word Julie. Julie is an online data management system specifically for electrochemical data. It works with, it's a standalone system, and it works with our SIA platform, our Sense It All platform. Now, the reason I bring up Julie is because what we do is we do a lot of testing at ZP. We analyze at quite fast scan rates and using a redox reporter. We analyze all of our electrodes by cyclophotometry just to get a sense of actually, are they reproducible and will they give electrochemical data? Now, I know there's lots of manufacturers out there and, they will also make these same statements as well. But I generally think that if you ask to see their data management system, ours is called Julie. You can go online, find Julie. You'll find it's a very powerful system. You'll find that we're the only people with a data management system specifically for electrochemical data. And we built it originally actually to make sure that our screen printed electrodes were reproducible. So we do a lot of analysis on our electrodes. We measure the mean peak height, we measure the standard deviation, we measure the relative standard deviation, and we're always aiming for less than double digits relative standard deviation, because the people who benefit the most from good reproducibility of ZP screen printed electrodes is Zimmer and Peacock. We are the biggest users of our own electrodes by far. We use them in our own products, and we use them in the programs that we run with customers, and we then actually sell them also to the academic community, through our online stores. But that means that the reproducibility is really good. It's interesting actually, because the other day I was doing a webinar and a client was saying, "Oh, I hope you've improved your reproducibility." And I realized that there's always a next step when I talk about reproducibility, and that's really the lab skills of the people who are then using our screen printed electrodes, and that's a tricky one for us because a lot of the time, maybe, reproducibility sometimes people are actually learning the art of doing experimentation on screen printed electrodes. So if they're sometimes suffering from reproducibility, it actually might come down to them. But we do definitely test electrodes and make sure that they are reproducible. And if people want to buy essentially samples, they go on the website and use them. If you're truly going to use, let's say, screen printed electrodes in a product, you need a quality agreement with whatever supplier. But with that, at ZP, we want people to be well funded and to be able to pay to have that quality agreement put in place. But that said, you can buy samples of our reproducible electrodes off the website. Just a quick link to the ones that these are our top 5 selling screen printed electrodes, and any kind of links you see I'll put underneath the video. Now I'm just going to change direction slightly. At ZP, we're very interested in electroanalytical sciences. I actually started my academic career, if I can call it that, doing things like electrolysis. And if you do electrolysis, you're also quite interested in things like flow batteries as well. And I realized actually my supervisor was super interested in redox flow batteries. I've always been quite interested in them as well, because I'm quite interested in flow. I'm definitely interested in electrochemistry. Who's not interested in power generation and power storage? So the redox flow battery is actually quite a useful device. Now, it's got 2 modes. It's got a mode where it can discharge, so essentially it's in a high energy state and it can actually discharge essentially electrons, and in discharging electrons you get the flow of current. Flow of current is doing work. So in this particular case, we're pumping vanadium 2+ ions through one half of an electrochemical cell, and vanadium 2+ really wants to become vanadium 3+. So it's essentially being oxidized. Now the electrons are leaving the vanadium 2+ and actually going through an external circuit, and in doing that they're then able to do work. So a vanadium flow battery, the pump pumps the vanadium 2 plus. The vanadium 2 plus is oxidizing to vanadium 3 plus, and in doing so there's a flow of electrons, and those electrons have to go somewhere, and they actually flow into the second half of the cell, but they will then do useful work on the way. And what's happening is we've got vanadium 5 plus being pumped in the other half cell, and vanadium 5 plus is actually being reduced to vanadium 4 plus. So on one side of the cell you got vanadium 2 plus being oxidized to vanadium 3 plus, and in the other side of the cell we got vanadium 5 plus receiving those electrons and becoming vanadium 4 plus. So vanadium is quite an interesting element in the fact that it's got all these oxidation states available to it. So we've got a discharge reaction where vanadium 5 plus in one side of the one half cell is becoming vanadium 4 plus because it's receiving electrons, and we've got another half cell reaction where in fact vanadium 2 plus is becoming oxidized and forming vanadium 3 plus. And this is essentially electrons are actually getting transferred through the external circuit, and that transfer during discharge is actually doing the useful work. Now, vanadium batteries are actually quite useful because then they can actually store charge. So I think people imagine them being used in sort of microgrids. You know, let's say you're kind of generating electricity 24/7 because it's a hydroelectric system, but yet the requirement for electricity is actually lower during the night or something. Then you can actually store using a vanadium flow battery and then a vanadium redox flow battery, and then you can actually, let's say there was a lot of energy requirement the next day at like midday because there was a high energy demand, then you could actually augment power by actually getting the battery to discharge. But in its charging mode, it's essentially running the electrochemistry in the reverse direction. Vanadium 4 plus is actually giving up electrons and becoming vanadium 5 plus, and in fact vanadium 3 plus, I think it is receiving electrons, becoming vanadium 2 plus. So in charge mode, you're essentially having to put energy into the system, and you're reversing, you're putting V4 plus into V5 plus and V3 plus into V2 plus. So that's the kind of that's the kind of storage of charge. Storage of charge is also like the same way as saying the storage of energy. So the vanadium flow battery has sort of two modes, charge and discharge. In discharge, you're getting useful work out of it, and in charge, you're storing energy, which you're expecting to discharge later on. The reason I'm kind of quite interested in vanadium flow batteries is this is definitely sort of an idea that I had a long time ago, where actually with flow batteries you can kind of calculate the state of charge because you kind of know what the current was at any one time, so you could try to guess what the state of charge is of a battery. But in fact, you could actually measure it, and you can, for example, measure the ratio between vanadium 5 plus, vanadium 4 plus, vanadium 2 plus, vanadium 3 plus by a technique like cyclovoltammetry or open circuit potentiometry. And I've been showing today in a demo, and I'll do a sort of another run through in a minute, that actually we have a very small potentiostat that if you were able to sample from the two half cells of the vanadium flow battery, you can actually calculate the state of charge. Sorry, you can measure the state of charge at any one time. And the nice thing about our system is you could actually turn that sort of ratio between vanadium 5 plus and vanadium 4 plus, or vanadium 2 plus and vanadium 3 plus, into an actual state of charge calculation or a ratio of charge calculation, and actually give the operator of that flow battery a real number, like a fuel gauge, as opposed to just voltammetric data. So I'll just sort of illustrate what I actually mean. Well, I'll talk through what I mean by that now. So earlier on I did a demonstration I talked about LEDs, and I was talking about how we can translate scientific papers actually into what the term I actually would often use is minimally viable prototype, an MVP. Now in this particular case, if you were trying to measure the ratio of V5 plus to V4 plus, you could use techniques like linear sweep voltammetry, cyclovoltammetry, square wave voltammetry. I say techniques like it because actually you would want to optimize and find out which of these techniques was actually the best technique for you. I suspect it would end up being square wave voltammetry. But what's nice then about this data pipe is once we've done that kind of calibration of different amounts and different ratios, you've actually ended up with a calibration curve. And then you can actually turn it into a meaningful value like state of charge, ratio of the different ionic states, call it fuel gauge. Because of the data pipe that we actually have built into the system, and I was talking about the data pipe earlier on when I did a talk through earlier on, but we have a way of, if it was cyclic voltammetry, for example, we could do things like find the peak height, put the peak height through a formula, and then actually turn it into, in this particular case, a concentration. But whoops-a-daisy, I realized I just did that, and in fact I didn't share my screen at all. But I'm just sort of saying, let's say we were talking about vanadium, the state of charge of that vanadium flow battery. We are quite capable of going back into this, into the cloud part of our data stack, finding the peak height, putting it through a calibration curve, and turning it, in this particular case we turned it into concentration, but we could turn it into something meaningful like concentration of vanadium 5+, or ratio between V5+ and V4+, or state of charge as well, or fuel gauge reading, let's say. So vanadium redox flow batteries, super interesting to me, and sort of I've been having an interest in them because I'm actually quite interested in making or working on fuel gauges for those kinds of batteries. Something else, we at ZP we do a lot of Aptamer. Aptamers are very popular these days, actually. In fact, it's interesting actually because I was making some comments about MIPS earlier on and saying that they can be quite problematic. I think all biosensors can be problematic. I think we sometimes make progress quicker when we're using things like aptamers. Aptamers and MIPS are for different, let's say, jobs. But if somebody came to me and said, I've got an aptamer, I'd be like, yeah, hey. And if they got a MIP, I'm like, okay, it's going to be a bit harder. So that's just a personal experience comment there. But in this particular aptamer paper, this is definitely something that at ZP we're very interested in, which is the translation of experiments that otherwise have to take place on the lab or in a lab setting into point of care, point of need diagnostics. And this particular paper, I've put the title here. I'm not the author of this paper. I'm only using these images to kind of illustrate really the next part for me, which is translating these types of papers truly out of the lab and actually into a real setting. And that when I say that, the fact that we're genuinely able to, in this particular case, I think they were using square wave voltammetry. So I'll just scan square wave voltammetry. Whoops, daisy, that's testosterone. Square wave voltammetry here. The fact that we can actually take their lab protocol, translate it onto a gold, ZP screen printed electrode, or translate the biosensor that is, and then run the square wave voltammetry on this device, and then put the raw signal again through immediately. The system will actually immediately send their square wave voltammetry data up to the cloud. We can then process, the scan, tell it go and look for the peak height, in this particular window, fit it to a particular formula, display the result. Means that paper can then actually have the result returned, a concentration or a CFU, a colony forming unit per mil or per 100 mils, returned to the phone, so that person or the end user actually ends up with a meaningful value. So a big effort at ZP is the translation of scientific or academic literature into more impactful research by actually getting the assays out of the lab. And so in this particular case, they're using cyclic voltammetry, which is definitely a technique that we have on this particular instrument. That's square wave, and that's TAS. There's cyclic voltammetry. So it's definitely a technique that we have on this particular instrument. But what makes it really good is the way we have this workflow that you can put a sample on there. You can create apps for this, The apps will tell the meter what to do. The meter will give the data back to the app. It could be square wave cyclovoltammetry, impedance spectroscopy. We also have on this system as well. So let me just find EIS. There we are, EIS as well. This is a really 2024/2025 type of technology. Not menus, not large bulky instruments. This is something that's, dare I say it, really up to date. And then we have this system called Julie. This is Julie, which you can actually access Julie. You can just create free accounts on it, which will actually process the data and then actually end up sending, depending on the calibration and the units you decide upon, you will then be able to send back meaningful data to a smart device. And that really helps to translate papers that are otherwise at TRL3 into papers that, are sort of definitely out of the lab TRL5 type papers. And so research can actually have, let's say, more impact. So that's definitely been a passion at Zimmer and Peacock. And this is something, I know I brought this up earlier on, but this Richard Compton paper that I kind of showed earlier on, this is something that we have literally been working on for 10 years. And I actually started working on this translation of academic research into meaningful, impactful research, let's say, 7 years ago at least, because in fact 7 years ago is when we first translated this particular paper into a product. And if you're looking for the outcome of all that effort, here it is. So sometimes people don't underestimate. Now, what makes this really possible actually is, this is an elegant instrument. It's got a lovely user interface, the way we got QR codes. So it's not all these menus. We've got a nice user interface that you can take these kind of electrodes, be it gold, platinum, carbon. You can flick them in, they make electrical connection. So that's also nice, especially if you're working with real samples like water. We have a little technique like this where you can actually pull that out, clean it out. This is much more robust than, this is the most robust electrochemical connector is out there, because we've dealt with a lot of potentiostats. They have these slots and etc. on them. And actually they break really quite quickly, especially in the hands of non-gentle scientists. So we have a very elegant way of cleaning it, putting it together, making an electrical connection. And then this, it's funny, I sometimes don't make the point maybe well enough, but this device is actually in Bluetooth connection with this device. So I'm just going to connect to it now. So they're actually in Bluetooth connection with one another, and that's what makes it, let's say, super smart. So there it is. And I can make Bluetooth connection with that. And that's the elegance of what we're doing. So, whoops-a-daisy, I mean to be going to this one here. Yeah, so there is a problem that we're trying to solve at ZP, and I've mentioned it earlier on, and I'll mention it again now. There are 25,000 papers that are kind of, coming out, which, I always like the electrochemical literature because it's very targeted, and at least the electrochemical sensing literature, that it's trying to solve real world problems. But there is actually a lot of papers being produced. They're not translating out of the lab into the real world, and this is the first commercially available instrument that really actually tackles that. And so, and it's actually, the reason I'm bringing it sustainable is because ZP is a commercial company, which means that the fact that there is, a company behind this does actually mean it's sustainable. People talk about sustainability, but if the sustainability disappears once the government grant stops, then that's not really sustainable. So unfortunately, sustainability in part comes from having commercial organizations involved. If you're interested in this, please come to our webinar on the 10th of December. You can also just contact me anyway. I'll put a contact link underneath. Now I'm coming to one of our other questions, which is somebody's interested in our potassium sensors. Our potassium sensors, like many of our sensors, kind of follow this kind of form factor, just to give you a sense. Actually, we do have all sorts of form factors. Whoops-a-daisy, I missed the questions. I was going too quickly. Will it be possible to detect potassium during the procedure when blood is given to the patient? Yes, it is possible. These things are possible. The real answer to this is, in order to make any medical diagnostic or device, there has to be, in the end, you will end up spending millions of dollars of money. So when I say yes, it is possible, ZP absolutely works on making medical diagnostics and medical devices for people. We are ISO 13485, so we are certified for this. But when big companies ask me if it's possible, the answer is yes. The question is, how much funding have you got at this moment in order to do it? So let's say you were really trying to make a device that was going to inject or return blood to a patient, and you said to me, you know, oh, well, my funding's €3,000. I say, please don't start it. You're going to endanger patients. You can't afford to take the, proper, you can't afford to take the proper steps here. And most of the ZP sensors, if ZP has over something like 40 sensors on our website, most of them are designed for continuous usage. If you design a sensor that's designed for continuous usage, you can also use it in discrete measurements as well. But let me just answer this continuous usage. Here's the data on our website. So here's a potassium sensor. Here we put 4 millimolar solution onto it. Then we put 5 millimolar solution onto it. Then we put 6 millimolar solution onto it. The x-axis here is time, by the way. So we're putting different concentrations of solutions onto that sensor, and then taking them back off again and putting new concentrations on. So we're basically doing what I call a staircase. We're running with time, and with different times we're adding different solutions or different concentrations of potassium rather, and you can see the potassium the signal changing with potassium concentration as we do it. So the answer is most of the ZP sensors are actually designed for continuous usage. But that means you can then use them in a discrete fashion as well. Just put a sample on them, get a result, bang, there you go. When I say most, I mean there is sensors where it's one-time use, but if by looking at the raw signal, you can see that this potassium sensor is actually used in a continuous mode of operation. But I'm very, very hesitant to be pulled in by any companies who want to make medical products using our sensors unless they've demonstrated the budget and they're well funded. Because as soon as somebody says to me, I want to use your potassium sensor in testing whole blood, that's a real red flag to us. At ZP, we will do those kind of projects that are well funded, have proven funding, and then we can use our ISO 13485 system to make sure that the patient's not at risk. Otherwise, when you check our terms and conditions on the website, you will find out that we will only sell these sensors really for R&D purposes only, because some rogue scientist somewhere will end up hurting patients, and we can't have that. Just FYI, if you want to do some proof of principle with potassium sensors, you can get sensors off ZP, you can get electronics off ZP, you can get test solutions off ZP, you can get rinse solutions off ZP, and I will, essentially these links will be underneath this video at the end as well. And I'll also probably put a bit of a landing page. Somebody's interested in making a troponin eye sensor. I would definitely say if you're a university, do not get a troponin eye sensor from ZP. Will be essentially too expensive, I think, and really if it's a university setting, then you should generally build the sensors yourself. If you're trying to build a troponin eye sensor, you can use a carbon electrode from ZP or a gold electrode from ZP, but then you'd have to kind of put the troponin on top of it. ZP, when we make our troponin sensor, we've tested it in plasma. It is human plasma, but it is in plasma. So we haven't tested our troponin sensors in sweat or blood. I don't know if troponin I is also, I don't know if it's adequately expressed in sweat. I strongly suspect not, because I think the troponin I is actually starting from the heart. So, I mean, to get to the sweat, it's kind of, heart to blood, blood to interstitial fluid, potentially interstitial fluid to sweat. That seems like quite a lot of compartments between the source and the final sensing part. But that's my opinion, and I don't have the clinical expertise to answer that question. I can't answer the second question, which is what antibody did you use? So I have to say this because, at ZP, even though I'm a founder and director of the company, within a business, you would have every employee would have a confidentiality agreement, and so a confidentiality agreement would mean that I would not be able to give trade secrets out. So I can't tell you what antibody we particularly used, but I would say the one thing I'd say about troponin I is there are lots of antibodies and sources of antibodies out there. It's a very sort of done assay, let's say, so that means it's quite robust. So you really should be able to identify an antibody, tether it, obviously, to a ZP carbon electrode, ZP gold electrode. If you don't know how to do that kind of tethering, Maybe I can cover it in a future webinar if you contact me again, but I can't tell you what antibody we're actually using. Question number 9, I was asked, how would one translate a paper like this into a actual product that could be used outside of the lab? This is a good one because actually they're trying to detect nitrates in soil. Just FYI, I mean at ZP we do, when I'm talking about nitrates, we do have quite a lot of experience of nitrates. In fact, we have a nitrate sensor. Just trying to think where. Yeah, so we do have a nitrate. Yeah, I do have it on here as well. Good. Whoops, daisy, wrong one. But we do have a nitrate sensor. It's one of the QR codes that we have on the device. Let me just go back to here. So I'm going to talk here about translating into an actual product. So the first thing I notice is that this is using open circuit potentiometry. So if I go back to how we would translate this into a product, we do have open circuit potentiometry available on this. We are able to, we have open circuit potentiometry on this, so we are able to then drive the device through Bluetooth from the app. So I do want to actually make Bluetooth connection with this guy. There we are, so I'm connected now. So now I've done open circuit potentiometry. I'm in Bluetooth connection with the device. I know I'm now in connection because this was a flashing blue light, now it's a white light. At which point then, they want to do OCP, which is great because that's one of the techniques that we have. It's one of the techniques we use quite regularly. I'm just going to go back to this screen here. So they're using open circuit potentiometry. They describe how they do their particular assay. Now, many of our screen printed electrodes at ZP are 3 electrode systems, but the potentiostats are smart. So when somebody's trying to do a OCP measurement, they may only need 2 electrodes, and the device will essentially only measure the potential between 2 of our electrodes. It knows how to do it automatically. You don't have to program it. So I'm first of all, I'm referencing where I got this from, and I'm only using the images really to kind of illustrate how we would translate a paper like this actually into a product. So what we would do is I would probably take the 501 carbon electrode, functionalize it with their nitrate specific film or polymer. They also put a Nafion layer over the reference electrodes. So this, as I say, the potentiostat, we don't need the counter electrode in this particular case, but the potentiostat is smart enough that in OCP mode, it will know, even though I've got 3 pins in this particular device, it will know to actually only use 2 of the pins, and it knows which 2 pins to use. It uses our working electrode and our reference electrode, because we're very consistent in that when we're sort of programming the devices and the way we do assay development. So if I was translating this into, let's say, into something that I could scale up and give out to other people, Nafion on here, and then they do have this interesting extra layer that they put on here, which is PVDF. And as I say, if I was kind of just do a quick summary demo, which I will do here. Let me just think when I'm going here. Right, okay, so we've got something called a 501 carbon electrode, which has a circular electrode. It's not this one, so the circular electrode is quite good because they can functionalize that quite readily. They can put the Nafion on the reference, their nitrate cocktail on the working. They can add that extra layer of, I think it's called PVDF on there. And essentially that point they made their biosensor. Then to actually run the assay, they can use the open circuit potentiometric mode, and they can then, I'll just do that anyway. This will give me rubbish because I haven't actually put a liquid sample on there. But it will essentially run that, and then when it's run it will actually upload the data straight to the cloud system that we got earlier on. Now I'm showing you here cyclovoltammetry data, but this can receive cyclovoltammetry data, linear sweep voltammetry data, square wave voltammetry data, EIS voltammetry data, OCP, open circuit potentiometric data, amperometry, and then actually they can put their OCP data again through the data pipe. Now in their case, they're not looking for peak height. They're probably just going to do a sort of measure the potential at a certain time kind of. By the way, that's uploaded the data to the cloud. They can come up with their own calibration routine. And in fact, that is a good point for me to translate, not translate, but transition, because in fact, with these kind of papers, they often have already done the calibration. So it's definitely what we're trying to help the academic community do is actually get from a proof of principle like this, a TRL3, where you did the testing in the lab, to TRL5, where you can actually take it out of the lab and actually put it into the, let's say, the, into the real world. And it, again, I mean, this is something that we started doing 7 years ago, and we actually turned this particular paper, let's say, into a product. And I say this, and it does, again, part of this, how do we convert more paper, especially things like nitrate in soil, which is a real, let's say, problem. And therefore, the market is self-identifying. Governments are very interested in this. If we want to reach kind of net zero in the world, nitrate's a good place to start, because I think 1.2% of global CO2 probably comes from nitrate production. So it's a good target. You wouldn't have to persuade many people that this was actually a good idea. If you're interested in this kind of work or this kind of translation, then do come along to the webinar on the 10th of December. If you're watching this video after the 10th of December, that link will take you to the most recent. So today I've talked about using the sensor or potentiostat for detection of lead in water. I've talked about ZP does have screen-printed electrodes with Streptavidin modified on them. I'd also say that if you're interested in doing Streptavidin linked bioelectrochemical assays, just get a carbon 501 or a hypervalue electrode from ZP and use those. We can translate pesticides papers into impactful products. If somebody's interested in using creatinine detection using gold electrodes, then the data, at least I've shown you today, our repeatability, our relative standard deviation is about 3%. I did explain the vanadium flow battery to you, and also say that I am interested actually in the fuel gauge or the state of charge in vanadium flow batteries. Aptamer chemistry or Aptamer biosensors is something we do quite a lot at ZP. Potassium sensors, we have them. I don't want people to just buy them off our website and start using them in blood. That would break the terms and conditions, which say that the sensors are freely for R&D purposes only, and people have to engage us in a really meaningful way if they want ZP to be hands-on in their medical diagnostic, medical device development. Troponin I've given you what I can give you, which admittedly wasn't an awful lot, but I'm also bound by confidentiality to my company. And then I think just lastly, the translation of that nitrate sensor paper into into something that's sort of more like a TRL5 is quite straightforward with that Sensei All platform. If you've got any questions, I want to say don't hesitate to reach out to us. I must admit that was awfully long, and my apologies for that. But I'll stop now, and as I say, any questions, don't hesitate to reach out to ZP. Okay, thanks very much.